Welcome to another RollCall breakout call. Today, we have a very interesting episode. We have Justin Drake here to host and lead the call on basically all things shared sequencing, preconfirmations, based rollups, basically this entire theme complex that he's been thinking about quite extensively. I'm very much looking forward to that, and I'll just hand it off. I mean, I don't think I have to introduce Justin much. He's one of our star researchers at the Ethereum Foundation, has been doing a lot of work in this in the past. And yeah, Justin, do you just want to take it from here?
Yes, thank you, Ansgar. So yeah, today we have a lot of time, an hour and a half. So I hope to make it very interactive. This talk is really for the rollups. So Ethereum sequencing and shared sequencing more generally is all about rollups opting in to some sort of shared sequencer. And I think there's a bunch of technical issues that we can discuss, but I think the bulk of it is actually an education and a coordination and an incentives problem, more so than the technical one. So I hope to go through a lot of content, and please interrupt me as the presentation goes along.
Justin, maybe if we can wait a few more seconds, because someone just mentioned that the Zoom link was never actually shared in the Telegram group. I just did that, but it could be that a few people might need a few seconds to see that and come on.
Okay, perfect. Let me know when it's good to get started.
Yeah, you can probably go ahead.
Okay, perfect. Thank you, Ansgar. So the talk will be split into three parts. First, I'll talk about shared sequencing generally, and in my opinion, the killer feature of shared sequencing, which is synchronous composability. And then I'll talk about preconfirmations specifically, because I think preconfirmations is a feature that every single rollup wants. It's a feature that users demand. And there's a question of how do we do preconfirmations in a decentralized setting as opposed to having a centralized sequencer. And then finally, I'm going to talk about base sequencing, which is a special type of sequencer, which also has these decentralized preconfirmations. So one of my, I guess, visions is that we have these united chains of Ethereums, similar to a union of states like the United States, where there's freedom of movement and freedom of commerce. I'm hoping that on Ethereum, we're going to have this diversity of chains, of rollups and validiums, but the friction from moving from one to another, the friction of doing business with one another is extremely low. And I think in order to achieve that, we need shared sequencing. So what is the killer feature of shared sequencing? In my opinion, it's this idea of synchronous composability. So if right now what we have is independent rollups that are siloed. And what I want you to think about is basically time progressing from top to bottom. So execution in rollup A is siloed from execution in rollup B, which is siloed from execution in rollup C. And one of the things that shared sequencing allows is for synchronous composability, meaning that for some period of time, you actually have the rollups be synced with each other. You can think of it as locking from the perspective of state. Basically, if a user finds it valuable to have synchronous composition across multiple rollups, what I call a super transaction, then they have the option to pay for that privilege. And the shared sequencer, who has monopoly power to build blocks for all the rollups in parallel, can actually fulfill this demand from the user. And so in some sense, shared sequencing is about going from asynchronous composition to synchronous composition and kind of capturing this delta of value creation in the process. And the synchronous composition doesn't have to happen at the very top of the block. It could happen midway through the block, and it doesn't have to be something that is permanently happening. And actually, almost by necessity, we can't have every single rollup locking on every single other rollup. Otherwise, we would only have the scalability of a single rollup. So what I expect will happen is that the vast majority of the time, the transactions will consume resources in one single rollup. Everything will be processed in a purely parallel way. But then every once in a while, when there's some sort of an economic opportunity that mandates that there's actually additional value to synchronous composition, then there's going to be these virtual locks that are basically placed by the shared sequencer on these executions. So if we zoom in to like this little section of the diagram, so we have the two rollups, rollup A and rollup B. What do I mean by synchronous composition? So I'll basically give an example. Imagine a super transaction, which is made of 3 sub-transactions. So you have a sub-transaction A, which kind of starts the super transaction. And then you have this middle sub-transaction on rollup B. And then you have this final sub-transaction on rollup A. And the important feature here is that like there's these strong synchronous relationships between these sub-transactions. So for example, you could have a withdrawal of asset here from A to B. You could have a withdrawal of asset from B to A here. You could also have some action here on rollup A, which depends on the result of a call on rollup B. So for example, here you could be reading some state on rollup B, and then you're basically passing some sort of state route to rollup A, and then depending on what's happening here, you do an action here. And one of the things to notice here is that in order to have these synchronous kind of calls between rollups in a totally trustless way, meaning that rollup A shouldn't be able to trust B and rollup B shouldn't need to trust rollup A, you basically need ZK proofs. So this sub-transaction here produces some sort of proof. It's settled immediately. There's a withdrawal. And then same thing here. When this sub-transaction here executes, there's a corresponding ZK proof that allows for this withdrawal to happen immediately. Or if you're reading data, same thing, it happens immediately. And then now they can have an action that depends on this data. And once you have this kind of really luxurious setting of synchronous composability, which we enjoy today at layer 1, right? Any contract can synchronously call any other contract. Then, in my opinion, you're unlocking a value. So yeah, feel free to stop me at any point in time if something is confusing. Now, one of the things that we need to ask ourselves is around these zero knowledge proofs that I talked about. Like, it takes time to produce zero knowledge proofs. And so let's look at a specific example. Let's say that we want to do synchronous composability within these 3 rollups at the very top of the block. So it turns out to be the simplest case. And the reason is that, let's say we have the shared sequencer has 12 seconds. That's the slot duration. It doesn't have to be 12 seconds, but let's assume it's 12 seconds. Well, if this the computation here, let's say takes 1 second, well, basically you have 11 seconds to produce the proof. So for settlement, I mean, all the zero knowledge proof for settlement. So here you have quite a lot of time to produce the zero knowledge proof. But on the other hand, here at the very bottom, if you want to do synchronous composability, like very, very close to the end of your slot, then you have almost no time to produce the snark proof. And so what I expect will happen is that initially the synchronous composability will be kind of more towards the top of the slot. But then as we get faster and faster proving, it will unlock value towards the end of the slot. Like, notice that the colored execution, which kind of doesn't depend on execution from other rollups, it's okay for the proof to come in the next slot. It doesn't have to come in like immediately in the current slot. Now, one of the things I want to highlight is that I'm extremely bullish about low latency proving. I think that within the next 2-3 years, go ahead.
Can I interrupt and ask
Yes,
why?
for sure. Yes.
Why it doesn't have to come in that slot?
Right. Sorry, I need to configure my Zoom so I can see who's asking a question. But why doesn't it have to come in that slot? So the reason is that, so just like today, you basically have a decoupling of you can have a decoupling of the data and the proof. So you can post the data on chain, and then settlement can be delayed some number of slots. And basically, if you have a rollup which is progressing independently, meaning that the execution doesn't depend on inputs from other rollups, then it's actually okay for the settlement to be delayed, because it's just like the same situation as today, where you can put the data and then you can prove it later on.
Yep. Thanks.
But as soon as you start depending, basically you're adding these dependencies between rollups. Well, if you want things to stay trustless and you don't want to do like these massive reorgs and rollbacks, then you need this real-time proving to keep the trustlessness.
I have one more question on this trust. So if we have rollup A and rollup B that have this cross-chain, cross-rollup transaction, but rollup A did not finalize the blue blocks because one of the previous block is invalid, and this we will learn like a while after the block is produced, because the finality in the rollup is not instantaneous. It means that the block is reverted. So for rollup B, we will have a dependency on rollup A for its own finalization.
Right. So that's a good point. Like you need basically fast settlement. So what I'm claiming is that either you need real-time settlement, meaning that you have settlement in the current block, or you can delay it to the next block. So basically, if you're the shared sequencer in slot n, then you can mandate that the shared sequencer in slot n+1 needs to provide the proofs for the execution that hasn't been proved in slot n. But yeah, you're right. Like we don't want to be building on top of unsettled rollup execution, and so like at most you want the proof to be delayed by one slot. But one slot today seems like very, very short, right? Because these zero knowledge rollups sometimes take minutes or sometimes hours to produce a proof, but we're getting that at a very, very fast pace. So I guess there's two types of real-time proving. There's real-time proving on the order of one slot, and then there's like the super, super fast real-time proving on the order of milliseconds. And I think we're going to see this first type of proving happen relatively quickly, like maybe this year even.
Okay, thank you.
Now, why are there like reasons to be optimistic about real-time proving? One of them for me is this notion of folding schemes. So Nova, which is a paper published in 2021, and it was largely ignored for a couple of years, is kind of in some sense a revolution in my opinion, because it allows for maximally parallel and maximally efficient snark proving. And it kind of led to this whole class of literature around folding schemes. And in my opinion today, if you're working with elliptic curves, then like it's almost a no-brainer. If you're starting from a fresh code base, it's almost a no-brainer to start with folding schemes, given like how mature they are and how efficient they are. They seem to be efficient not just asymptotically, but down to the constant. So basically, if it's roughly speaking, the prover cost is 1 MSM of the size of your statement. That's it, just 1 MSM. So the constant is 1. You can't improve it, and there's no FFTs, and it's a really nice proving scheme. And then the other reason to be kind of bullish on low latency proving is that we're starting to finally see proving ASICs. So the first one was released this year, this month, actually, by Axial. But there's 2 other teams, SciSig and Fabric, that are also working on ASICs that should come this year. So basically what these ASICs will unlock is like this really like super low latency, like 100 milliseconds or less. And so you can have synchronous composability very, very close to the end of the slot here. Okay, part 2, unless there are questions regarding part 1.
So yeah, I have a question. So 100 milliseconds you mentioned per block or per transactions or per super transactions?
Yeah, so basically what I expect will happen is that these proving schemes will operate on the order of like 1 cycle or 1 opcode, like some very small amount of computation, and then basically use this recursive technique to process 1 cycle at a time. And what we need is that the proving latency is on the order of 100 milliseconds. So the proving will happen in real time. So as the sequencer kind of chooses which transactions to sequence, as execution happens basically and sequencing happens, in parallel, the proving also happens. So actually, as a consequence of this, I think it's relatively likely that we're going to see a merging of the sequencer and the prover, so that you have minimal latency between these 2 things. And what you want is the proof system to have very low latency. So from a throughput perspective, obviously you need to have the proving capacity to prove 12 seconds worth of execution within 12 seconds. Like every single rollup does that, otherwise the prover would start falling behind. But now that we can catch up in terms of throughput, we need to kind of optimize latency. And I think there's already like massive strides that are being done on that front, but I'm expecting way more in the months and years to come.
Thanks.
Okay, great. Now, one of the open problems, a couple of years ago was how do we decentralize preconfirmations? Oh, Mohammed, do you want to ask a question?
Sorry. Yeah. I was wondering, why do you need these proofs really real time? Like, suppose you have a super transaction and it calls into the other rollup and it expects something back. Why we can't provide this, like intermediate state or like value of the callback or whatever optimistically, and only at the
Yes.
end of the whole slot we prove the whole thing?
Yeah. So a few things here. Like one of them is that you do want to provide like 1 proof at the very end, just because like imagine that you're processing thousands of transactions per second. Like you don't want to have 1 zero-knowledge proof every time you make a deposit and withdrawal. So what I expect will happen is that for each rollup, there's going to be 1 proof, and it's going to be an aggregation of all the subproofs that you need in order to have all the execution. And from a computational standpoint, this proof will arrive at the end of the slot. But what the sequencer can do is that they can basically stuff it at the very beginning. So once they've computed it, and they build the actual block that goes on chain, they put it at the very beginning and they verify it first. So up front, they verify, they kind of make a claim that this execution is correct, kind of pre-state 1, post-state 1, pre-state 2, post-state 2, pre-state 3, post-state 3. So it's a proof about all these pre-state and post-states, 1 per rollup. And then nothing has to happen optimistically because it's all kind of proven up front. So does that answer your question?
Yeah, it's kind of answer, but like basically I was wondering, so the way I understood your scheme is that when a super transaction happens, we are going to have this micro snark proofs that assured you about what happened on the other rollup.
Yes.
Yeah, exactly. Yeah.
Yes.
So the green arrow back, I expect, is carrying a snark proof, or
Yes.
like.
So
Yeah, I was wondering why this is necessary.
Yeah.
I understand if you want to be really real time, like doing execution and proving at the same time, this is what you want, especially with Nova and folding this.
Yeah. So the sequencer has full control over what the sequence will be for rollups A, B, and C. So you're right, like they can work optimistically because they trust themselves, right?
Exactly.
So, you know, let's say that the proof latency is 2 seconds. Well, then, you know, for 2 seconds, they're kind of going to optimistically sequence things without a zero knowledge proof. And then the zero knowledge proof only comes at the very end. But if the latency is, let's say, 2 seconds, what it means is that in these last 2 seconds, there can't be any synchronous transactions. Like the synchronous transactions have to be in the first 10 seconds. Great, you have the thumbs up, which means that you're liking this answer.
Makes sense.
I guess one thing that I'll mention, which is really cool here, is that we're actually using MEV to incentivize low latency proving, right? Because one of the problems that ZK rollups have is like, how do we incentivize proving? And the really cool thing here is that sometimes you have to do nothing. Like MEV does the job for you, because the more latency, the faster you are, the less latency you have, the more synchronous composability you are going to be able to sell to users. And so that's kind of a nice property to have. Lisa.
Sure, I understood if this shared block will happen at the same time each slot, or it's kind of on demand.
Yeah, so it's on demand. And what I expect will happen is because there is an overhead to locking, the user kind of has to explicitly opt in to pay for it, or it can happen implicitly if you have arbitrage or whatever. Now, one of the things that's interesting is how much do we expect users to have to pay? So let's say that here, you know, while this transaction on rollup A is executing, you see nothing's happening in rollup B. It's like this black stuff. So rollup B is basically blocking on rollup A, and here vice versa, you have this transaction happening on rollup B, and rollup A is just twiddling its thumbs. It's waiting. It can't progress. And so what will happen is that, let's say this corresponds to 100,000 gas. And that this also corresponds to 100,000 gas. Then at a minimum, the user will have to pay 100,000 gas on rollup B and 100,000 gas on rollup A. So basically pay on both of them simultaneously, plus potential overhead for even just creating the lock in the first place. And so economically speaking, if you're going to be consuming resources on multiple rollups at the same time, you're going to have to pay for it. And if there's this blocking aspect, then yeah, you're definitely going to have to pay for it.
But
Andreas,
how then do rollups communicate with each other on agreeing that this is the right moment for a super block?
So the rollups are not in control of sequencing. The rollups are in control of execution, and they're basically delegating sequencing to some shared sequencer. And the shared sequencer for their slot, they have monopoly power to do whatever they want. And what they're going to do, in my opinion, is they're going to act rationally, and so they're going to try and sequence blocks in such a way that they maximize the value of the block. And they're going to use signals from users saying, I have such and such intent, and I'm willing to pay for it. And so they will honor these intents if that maximizes the value of the block.
But presumably they're maximizing their own revenue, not the value of the block, right?
Yes, they're maximizing their own revenue, but there's a very strong correlation between these two things. But yeah, happy to have this discussion offline for sure. Gottfried. Sorry, Andreas, you had your hand earlier. Sorry.
Thank you. Appreciate that. Really quickly, so when you lock, let's say you on the super transaction and B locks A, right? So then A has an opportunity cost of like up to 10 seconds, correct? Right? Because if you allow A to process any other transactions, that one of those transactions might modify the target state of the super transaction, right? Which can't be, because I need to rely as an issuer of a super transaction that my target state is not modified. Isn't that correct?
I didn't completely understand the question. Can
So
you repeat it?
So let's say I want to I see an arbitrage opportunity on like Uniswap on Arbitrum, right?
Yeah.
And I'm on ZK Sync, right? Just like let's make it really concrete.
Well,
and
A
I want
and
to
B,
use
Arbitrum and Base.
Yes, Arbitrum and Base, whatever. Yeah. So I want to move. I want to put a swap on Arbitrum with my funds from Base, right?
Okay.
But if so I submit that transaction with a commitment that it's going to be executed against the current state of the Uniswap liquidity pool at that point in time, because I'm like buying the now. That means that Arbitrum needs to identify all the transactions that are going against that liquidity pool during the locking period, right? And put them after that super transaction, because the super transaction paid for or is paying for the privilege of having locked target state. If that target state is modified by a transaction that happens during that lock period, then the user with the super transaction, so me wanting to do the swap on Uniswap, like gets a worse price. So you're basically doing you can do sandwiching attacks and front running attacks, right?
Oh.
If you see that, because you have to have, you have a shared mempool at that point, so it's like that gets really tricky. So you have to basically lock down the roll up for the super transaction for that period of time, or they must be able to identify the transactions that are coming in that target the target state. Otherwise you're basically telling the issuer of the super transaction, well, you know what, you paid for it, tough luck.
Okay, so I still didn't completely understand the question, but let me try and say something that hopefully is helpful, and maybe we can talk about this more offline. One of the things I'll say is that yes, there is some sort of shared mempool, but that doesn't have to be a public mempool. So just like today, when you have a centralized sequencer, there's no public mempool, right? The user and the shared sequencer are communicating directly with end-to-end encryption, and no one sees the transaction. And actually, as a service, the centralized sequencers provide MEV protection. And so one way that you can kind of replicate this, well, the end-to-end encryption with the sequencer is very easy, right? Because we're going to know who the shared sequencer is. And so there's going to be an IP address that you can call as a user or as a wallet. The other thing I'll mention is that you can use account abstraction to make sure that your intent is properly expressed. So let's say you have a super transaction which involves 3 legs. Leg 1 on rollup A, leg 2 on rollup B, leg 3 on rollup A again. And you might want like these 3 things to happen either all together or none of them. So basically you're creating some sort of super bundle. That's the kind of thing that you want to constrain as a requirement, so that you don't get unbundled. And one of the things that's really cool is this idea from Polygon called the aggregation layer, where you can do exactly that. Yeah. Another thing I'll say is that, like this super transaction should execute extremely quickly, right? On the order of, microseconds. Because, each constituent transaction, takes just a few microseconds. And so, there shouldn't be like multiple seconds of opportunity cost. But yeah, more than happy to continue this discussion offline. Gottfried.
Yeah, maybe it's a stupid question, but there is one thing that I'm wondering. I mean, in Ethereum, where we have synchronous calls, we have everything is on a single state, basically,
right.
And you have the opportunity to roll back in case of error. Here, if you imagine the situation like the one you have on the slides, where basically rollup A does something, passes a proof over to rollup B does something depending on whatever the proof says, then there's a proof going back from rollup B to rollup A. But now imagine that in the third transaction on rollup A here, there is some kind of error happening, and which would necessitate basically undoing whatever happened on rollup B. Is there any way that this can be sort of achieved without basically enshrining some kind of chain rollbacks?
Right. So, as I said, like with the Polygon aggregation layer, you can basically have these three sub-transactions, like either all execute or the whole thing's invalid, like each of these three are invalid. Now, if, let's say, the super transaction is invalid because the last leg happened to be garbage, then the sequencer is just paying for the data to get these three sub-transactions on chain, but it's not getting paid for anything because it will just be rolled back. And so really what the shared sequencer should be doing is that at the execution and sequencing level, they should build these optimal blocks and potentially reverting whenever the transaction fails. But then once it's like made a decision, I'm actually going to sequence this and I have confidence that it's a valid transaction, it's fee paying, then at that point, does the proving process start. And again, like you don't need the proofs to come in real time. Here, the proof basically needs to come by the time the block is published for settlement. So from a time perspective, it only needs to be generated towards the end of the slot here. Kalman.
So just to make sure, we are trying to enforce synchronicity on the protocol level and not just the economic builder level, right?
Only the economic sequencer and builder level, not at yeah.
Okay, thank you.
So each rollup in some sense is just the same as it is today. The rollups don't have to do, at least the ZK rollups, they don't have to do that much. They stay, sovereign and independent. There's no like polluting of security assumptions. If rollup A blows up and then the hacker withdraws everything, then rollup B is completely isolated. These are like totally trustless relationships. Okay, decentralized preconfirmations. So I was saying that, yeah, 2 years ago, I would have said this is an open problem, but in some sense, like there's this obvious solution, which makes sense. So the obvious solution is, let's imagine that we have a decentralized sequencer. What is the definition of a decentralized sequencer? It's one where at every slot you have some sort of rotation of who's doing the sequencing. So in a centralized sequencer, it's the same entity every single slot doing the shared sequencing. Decentralized sequencer, just like at Ethereum layer 1, you have a rotation of the layer 1 proposer. Here you have a rotation of who's doing the sequencing. But in any given slot, it's the exact same situation. There's one single well-defined actor who has monopoly power to do the sequencing. And so in some sense, it's the same situation as a shared sequencer within those 12 seconds. And so what a user can do is that they could say, okay, please pre-confirm my transaction and sequence it. And then whoever the shared sequencer is for this slot n, well, they can make a promise that they will execute this transaction at a specific position. And I use the emoji 1, 2, 3, 4 here because it's kind of ordering the transactions. And you have this look ahead here, which means that who will be the shared sequencer at any given future slot. But really, you only need a look ahead of one slot, right? Because the user at slot n only needs to know who the shared sequencer at slot n is in order to make this request and get a pre-confirmation promise. Now, the way that shared sequencing preconfirmations is done today is using reputation as collateral. So you might have some sort of entity, some sort of labs, maybe the team that built the rollup initially that has a lot of reputation at stake, like arguably like hundreds of millions. Their reputation is worth hundreds of millions, if not billions of dollars, because if they were to start rugging users, then all their users would leave and the value of their token would go down. But in a decentralized sequencer, that you don't have entities with reputation, and so you kind of have to use direct economic incentives with slashing. So basically, the deal is that if, as a shared sequencer, I provide a preconfirmation, a promise of a preconfirmation, and the user is not happy because their preconfirmation was not honored, then there's going to lead to slashing. And there's two types of slashing faults. One is a safety fault, meaning that as the shared sequencer, I promise to sequence, a transaction, but instead I sequence another one. So it's like completely different. What actually happened is completely different to what I promised. And then there's this more subtle edge case fault, which is a liveness fault, where the sequencer made a promise, but then when it was time for them to honor their promise and to actually build a block, they went offline. So they got really unlucky. Like within the few seconds that they had this responsibility, they kind of went offline. And here they also have to suffer a penalty. But that's more of an edge case. Then this first one should never happen. The safety fault should never happen if you have an honest shared sequencer and preconfirmer. Now, if you have one entity who has monopoly power over one slot, like a very natural economic outcome is for whoever has monopoly power to maximize the value of that slot, and that leads to MEV boost and PBS being one of, I think, in my opinion, like the most natural outcome. But various other people might disagree. But I'd like to keep that for a separate discussion. So, in terms of okay, how do we modify MEV boost to make it work with preconfirmation? So the way that MEV boost works today is that we have blocks kind of traveling in one direction. So the builders build the blocks, they give them to relays, and then the relays relay those blocks to the proposer. But now we have this new entity in the picture. We have the user, and the user has made, has received promises from the proposer, and really we want the blocks to respect these constraints from the users. And so what needs to happen is that these promises need to travel all the way from the user to the builders through the relays. And so what I expect will happen is that, sorry, this should say shared sequencer, not proposer. What will happen is that like the shared sequencer really should be communicating every single promise that they make to the relays and to the builders. And then at the end of their slot, they basically ask the builders, given all these constraints, build me the most valuable block possible. So it's possible that at the very end, there's some back running or something that extracts a little bit of MEV. And the builders are the most natural players to do that. And you just need to modify MEV boost a little bit. So again, there's no need for any enshrining or hard forks or anything. You just need to do a simple modification to MEV boost so that builders can be aware of these preconfirmations and build blocks that adhere to them. One kind of detail here is that if the sequencer is collateralized, let's say they have 1,000 ETH of collateral, that will back the preconfirmations. Well, the builders also need to be equally collateralized, and the reason is that the builders might build a block that doesn't respect these preconfirmations, and the sequencer will get slashed, and now the sequencer needs to get compensated by the builder because it's not their fault, and so the builder would also get slashed, but the slashing, the collateral would go to the proposer. And when the sequencer gets slashed, there's two possible things. Either you can just completely destroy the collateral, or you can have more of an insurance mechanism where you give it back to the users that were affected by these violated preconfirmations. Okay, so this is kind of my summary slide on centralized versus decentralized preconfirmations. The big difference is that with a decentralized sequencer, you have this rotating sequencer on a slot-by-slot basis. The slashing is reputational for centralized sequencers, and I think it will become like purely financial in a decentralized setting. And then kind of one thing that kind of changes pretty dramatically is how MEV is handled. So right now we basically have an encrypted mempool, which is potentially first come first serve, and because you can rely on reputation, you can have these policies that are enforced. But when you move to a decentralized setting, it's possible that these policies can't be enforced so cleanly, and so you fall back to PBS, at least as one of the options here. Which ends part 2. Any questions?
Just could you clarify what is the promise that a pre-confirmation is making to the user? Is it a
great question.
Is it a promise that their transaction will be in an L1 proposed block, or is it a promise that their transaction will be in the canonical L2 chain?
Right. So the sequencer has full control over the contents of the blocks, and so they can give the strongest possible promises available, which is a promise on an exact state route. So basically, I will execute your transaction, and when your transaction executes, this is the post-state route. Of course, the user might not need such a strong pre-confirmation. They might only need some sort of intent to be satisfied. So, for example, they want to know, they might place some sort of limit order, like I'm willing to pay X for this swap, and I'm willing to pay Y for fees, and like so long as you can satisfy this intent, then I'll be happy. Some users might have something even weaker, which is, as you said, just inclusion. Like if I'm doing a transfer, let's say a simple transfer of ETH from A to B, then I care about getting the green check mark on my wallet, but I don't care what the post-state route is, because my transaction is totally independent from all other transactions.
Sure.
Now,
I guess. Could I clarify the question? The question really is how can an L1 proposer guarantee inclusion in the L2 chain, right? What if their L1 block that they propose, which is consistent with their promises, turns out not to be canonical on the L1 chain?
Okay, so at this point in time, there's no L1. At this point in time, we talk about shared sequencing, and it's like some abstract virtual shared sequencer. There's not an L1. Like the L1 comes in part 3, where we talk about base sequencing. But the way that it works is that basically every rollup has opted in to give sequencing rights to this shared sequencer. And so by construction, like they have monopoly power to.
So the individual proposer has the power to make a block canonical?
Yes. Yeah, I apologize. It should not say proposer. It should say sequencer. So whatever the sequencer is, whatever black box has the rollups have opted in for sequencing, that entity here has monopoly power to sequence.
I see. So there's some kind of consensus protocol wrapped around this, and the individual proposer promises that consensus protocol will reach consensus on a block that contains this user's result?
Yes. Again, I apologize for putting the word proposer here. It should really say sequencer. There's no proposer. Forget proposers. This is a typo. The proposers come in part 3. So imagine it's a sequencer. Like all the rollups have given, through their settlement contract, the priority access for this sequencer to sequence transactions. And therefore that entity has monopoly power, and therefore they can give preconfirmations of the strongest form possible, which is preconfirmations on execution.
But if you have these rotating proposers or rotating entities, how can one of those entities make a promise that anything will be canonical in the consensus?
Right. Well, okay. One of the things that they can do is they can give preconfirmations that are conditional on some sort of parent. So that's one possible outcome. Like another possible outcome is that there's some sort of single slot finality, fancy consensus. And this is what Espresso was building initially, where you have this off-chain consensus with like ultra fast finality. And so I, as a sequencer for slot n, I have very strong confidence that slot n-1 will be canonical because it's been finalized in very low latency. Like these two approaches are kind of complementary. So you want fast finality because that gives you more confidence on what the parent is, but you also, as a sequencer, only want to give preconfirmations on the things that you have power over. Like you don't have power over what is canonical. You have, and so the preconfirmations can be conditional on the parent. Now, if you look at things in practice, you can design consensus algorithms where you have very strong confidence on what the parent is, meaning that with very high probability there won't be a reorg. And so there's basically two cases. Like the case A, the happy case, will happen 99% of the time, and the user will be completely happy. And then the 1% of the case, something weird happened. There was a reorg or mislot or high latency or whatever. And one of the services that the sequencer can provide is basically insurance against this 1% edge case. And so, for example, let's say the user wants to trade on Uniswap, and they want to know exactly how much they're paying, both in terms of execution price and in terms of fees. And they'll get that for 99% of the time. And in the 1% of the time where there was some strange event, a reorg, for example, the sequencer can basically provide a second preconfirmation on this other event where it says, I will actually guarantee you the same price. And if there's a delta between the two, I will pay it out of pocket. So I think from a UX perspective, it would be a bad outcome if every time you ask for a preconfirmation, there's these two cases. Like case one is the parent block is canonical, and case two, the parent block kind of got reorged and it's an empty slot. And the good news is because one of the events happens 99% of the time and the other one only happens 1% of the time, you can kind of abstract away this edge case with insurance. But one of the things I'll say here is that these are the kind of problems that need to be solved regardless of the shared sequencer. Now, I have a very specific thesis, which is that we should consider using the L1 as the shared sequencer, but and in some sense, like all of these details around preconfirmations are details, implementation details that are orthogonal to the broader thesis, I guess, of base sequencing. Connor, you have your hand up.
Hey, so yeah, just in this case specifically, I guess in this there won't be any value to capture for the builders in this shared sequencer case. So yeah, I don't really see why you need the proposer. Why you need the builder or the relay.
Ah, right, I see. So basically, what you're saying is that if transactions are kind of handled almost first come first serve, like they're kind of pre-confirmed in real time, then there's very little relevance for the builders, and that might be the case. I guess one of the possibilities is that the the promises that are made are kind of these weak and fluid promises. So for example, like I promise you a certain price, but I don't promise you a certain position in the block. And so there could still be opportunities for builders to reorder things and like do some back running and do some arbitrage or whatever it is, in order to just squeeze out a little bit of drop of MEV. But you're right, like maybe this is not worth it, and we can just radically simplify and just remove the relays and remove the builders and only be left with this sequencer.
Sorry, so you're moving to a intent-based shared sequencer is what you're saying?
Yes, I mean,
No, sorry, that's a joke. It's a joke.
I think intent, yeah, makes sense. And actually, one thing I'll say here is that if you're providing promises on execution with a post-state route, then this is extremely non-scalable. And the reason is that the user comes in with the requests, it requests a specific post-state route, and that's blocking. So if it takes 100 milliseconds just for the communication between the user and the sequencer, then you can only process one transaction every 100 milliseconds, which is really bad. And so at the minimum, you want access lists, right? So that every user only cares about the little piece of state that they read and write to. But you can do even better, where sometimes you don't care about the exact value of the state. You only care about some intent, some abstract intent being satisfied. Payment.
Hey, could you please go to the next slide?
Yes.
Yeah, in this one, in the MEV one, I'm pretty confused about, because like you mentioned that for centralized sequencing, we have like encryption, and for decentralized one, we don't need encryption, and like PBS works. Right. But to me, like they are not really exclusive. They solve different problems with, like, I don't know, encryption, we have execution privacy, and like PBS can work for both of them. Like, yeah, just wanted to hear your thoughts.
Okay, let me clarify. You're right, this is sloppy. So in both cases, the user is dealing with a well-defined entity for that one slot, and they can use SSL to have end-to-end communication. So I guess SSL should be there in both cases. But the real difference is in terms of incentives. So the shared sequencers, so for example, the decentralized sequencers, I don't know, off-chain labs or something, like they don't want to be rugging their users. They don't want to be sandwiching them. They don't want to be exploiting them. And so they've just decided, as a policy, that they won't be extracting this type of toxic MEV. But in a decentralized setting, it's much harder to enforce that. Like what tends to happen in decentralized settings is that like you have these much more like locally rational actors that in this one slot I want to maximize as much as possible because I only get selected once every few months, for example, and I want to make the most of the slot that I just won. So in some sense, like we're playing different games. Like in the centralized case, it's a repeated game because every single slot is the same entity, and like there's these indirect incentives with like billions of dollars of tokens. Whereas here in the decentralized setting, like you can analyze the incentives on a kind of microeconomic level as opposed to a macroeconomic level. And as far as I can tell, like if you want to maximize the value of your block, then you're gonna invoke PBS in some way or another.
Yeah, I guess like my confusion was like you mentioned, like encryption is for centralized and the other one is like for like decentralized. But in centralized one, as long as you are putting your trust in like Arbitrum sequencer, you don't need like probably encryption with or like PBS. But in decentralized setting, like you can have encryption for preventing like toxic MEV, because just PBS doesn't prevent toxic MEV. And having like top of block auctions, right, for like good arbitrage and like good MEV. So basically both of them are for decentralized setting, and for centralized you can have some kind of separation for the powers of the centralized sequencer, but it's not like necessarily the need.
Right. I mean, the MEV protection here is provided using trust and reputation. And if you want the same kind of safety, then yeah, you might want a system where the sequencer never sees the plain text of the transaction until after they've done the sequencing. So you could have a threshold decryption or delay decryption or SGX-based decryption or whatever it is. Yeah, totally agreed here. But again, like this is a problem with decentralized sequencing in general, and in some sense, it's not my problem, even though I am, happy to help solve it. Like any decentralized sequencer, as far as I can tell, has this issue. Lynn.
Yeah, I have a question about the safety fault slashing. So when you, I can see that you can slash like when you promise to be in like the third slot of a block, and you can slash that. But what happens when a preconfirmer lies about the state? Like, how do you slash that on chain? Do you require some on-chain fraud proof, or
is there
on-chain some better way?
Yeah,
so, like,
I mean, even for the promise that the position is number 3, you still need some sort of on-chain fraud proof. So basically, what will happen is that when the user receives the promise, they receive a cryptographically signed receipt, and then the receipt is the fraud proof that they submit on-chain.
Yes, but like for state, you actually need knowledge about the VM to actually like verify the fraud proof. So it sounds like for every single VM, for every rollup, you need a fraud proof system for them, and it sounds like a pretty complex thing to implement.
So no, the fraud proving and the preconfirmation like collateral can be separate. So you could have n rollups that have each opted into a shared sequencer, and then you have this additional contract for preconfirmation specifically, and like this contract can read state roots that are settled. So let's say that the promise was, that this state root is X on rollup A, and then it turns out that rollup A settled state root Y. Then now the user can submit on-chain a receipt, which is cryptographically signed by the sequencer, saying that he promised that the state root on rollup A would be X, but it turned out to be Y, and therefore he gets slashed.
Well, your transaction can be like between these settlements. So like the state root that the rollup of the sequencer or the preconfirm signed can be like in the middle of this 2 commitments. And
yeah, so you can unroll the state root. So once you have the post state root for the whole block, then that fully deterministically gives you the whole chain of intermediate post state roots, and then you can match.
So it's like Arbitrum style, like full blown fraud proof.
You can actually do it in a single round. So basically, you could have the user submits the receipt as a fraud proof, and then it's on the sequencer is now challenged to prove consistency of the receipt and what was settled, and that could be like a one-shot snark, for example. And so you don't need many rounds of interaction, just one round of challenging.
It could be simpler than that too. If the proof include a Merkleized, commitment to the intermediate states, then you just point to one of those and provide a Merkle proof and say this is my transaction, but the pre-state is something else.
Yeah, you could do it in like one shot. Like the user just provides a one-shot proof of malfeasance from the sequencer.
I see. Thanks.
POTUS.
Yeah, I also had a question about the slashing. I left it in the chat. I don't understand the difference between safety and liveness. If I hold two consecutive slots and I gave a preconf for slot n, and I just happen to go offline and I cause a safety fault in n+1, how much do I pay?
Yeah, that's a great point. So in some sense, from the point of view of the user, they don't care if it's a safety fault or liveness fault. Like they got rugged either way. I think it's just a bit of a technical distinction. and maybe also a probabilistic one, like this should never happen if you're honest. This will happen, but with low probability. And so yeah, I mean, one of the things you could do if you want to be super fancy is you could have some sort of consensus mechanism, like Espresso is trying to do, where the slot n+1 is constrained by the preconfirmations in slot n, even if slot n happens to be reorged. But yeah, I agree that from the point of view of the user, like these are both equally bad. And like one way to size the collateral is to think of the maximum value of a block if there was no constraints from preconfirmations. And actually, we have historical data on this from MEV Boost, which is that the maximum amount of MEV in any given slot is less than 1,000 ETH. So this is why I keep using the 1,000 ETH number, because if you renege on all your preconfirmations, then you can make up to 1,000 ETH in MEV. And you're right that if you have a missed slot at slot n, and now the proposer at slot n+1 can do whatever they want, then that's effectively the same as a safety fault. And so what I would do is I would also punish maybe the liveness fault for 1,000 ETH. But what I expect will happen is that these sequences will get sophisticated, and they'll be able to price this risk. That's one, but also they'll be able to minimize the risk of liveness fault. So on Ethereum L1, like the reason why there's missed slots is because people submit too late. That's basically the reason. And in some sense, it's the fault of the proposer, of the operator. Like in theory, you could have like these periods of like very high asynchrony with the attesters, but in practice, that basically doesn't happen. It's basically always the fault of the operator. And so if you have a lot of value at stake from missing a slot, then you're going to be damn sure that you're going to be online and you're going to submit your block on time. And we have Daniel with your.
Just wanted to hear a little bit of how you're thinking about the centralization of the builders, because right now we have, Polygon, ZK Sync, Arbitrum. In the future, we're going to start having more and more of these hyperchains or CDK chains or OP chains, and the sort of de facto situation starts being that any builder should start running every single chain that exists in the entire ecosystem to maximize their MEV, to maximize like the chance of them being able to propose. And I'm just kind of curious of your thinking behind that, because
yeah,
like you can't sort of like with MEV Boost, you can decentralize that, or you can distribute that with open source. With server resources, you can't really distribute that. So it just ends up being a few entities in the world that pay a shit ton to be able to run these. And I just wanted to hear your thinking on that.
Right. So one of the observations is that you have extreme centralization, even if you have to deal with one virtual execution environment or one virtual machine. So if you look at the EVM, L1 EVM today, there's extreme centralization at the builder level. You have a Beaver build with like 40 or 50%, and then there's Titan and Rsync that have almost all of the rest. So basically 3 entities are controlling the vast majority of blocks, 2 of which are censoring, by the way. So it's not a pretty situation. What I'll say is that what we're trying to do is to design the consensus layer in such a way that the builders can't do harm. So, we can try and list like all the pieces of harm that they could do. Like they could censor, they could go offline, they could try and do all sorts of things. And it turns out that for every single bad thing that I'm aware of, primarily censorship, but there's other things that they could try to do, we have solutions for. So for example, inclusion lists is helps with censorship. And so one of my philosophy, I guess, is that we've kind of accepted, builder centralization as a natural market outcome, but we've segregated it from the validators. So we want to make sure that, for example, the centralization of the builders does not leak or pollute the validator set. So the validators can still be running on the Raspberry Pi, on a smartwatch. Like they need almost no computational resources. Now, one of the questions that is very reasonable to ask is, what if every chain has its own independent kind of PPS? And so now the builders only have to run one full node. Well, I actually think that's not kind of economically to be expected. And the reason is that the amount of MEV that you can extract is a function of how much information you have about the world. And in some sense, the builders, they want to be maximally connected to centralized exchanges, for example, because they have more and more price information. But they also want to be maximally connected to all the other chains because there's going to be economic activity happening there. And there's also going to be, interactions where there's going to be, bridges, and there's going to be asynchronous transactions. And not only that, even if the rollups don't explicitly opt into a shared sequencer, what we might see is a market of that kind of naturally emerges kind of at higher level, something like Suave, where the proposers can trustlessly sell, the sequencers can trustlessly sell their sequencing slots to the highest bidder. And in some sense, this mega builder, which builds all the rollups simultaneously, is an outcome that's going to happen either way, whether or not the rollups explicitly opt in to this. So my philosophy is that, I accept the builder centralization, but I want to make sure that there's no negative externalities to that centralization. The one thing that I will say that remains in terms of negative externality is mimetic, right? It's a really bad look that 90% of blocks are built by 3 entities. And I think the best answer to that is education, right? Making people understand that actually is not so bad, that because they can't cause liveness failures, they can't cause safety failures, they can't do front running, they can't do censorship. But yeah, it's going to be an uphill battle. And in some sense, it's similar to the centralization of the mining pools in Bitcoin, right? There's 3 mining pools that control everything. It's really a bad look for Bitcoin, but they moved on, and whoever's interested in Bitcoin understands that actually the mining pools don't have that much power in the grand scheme of things.
I guess the only concern is it removes the optionality of me being a medium block builder. I understand the centralization. I understand if we can stop censorship through CR lists, if we can have right. Threshold encrypted mempools, I understand these concepts, but it removes the option of me being an irrational economic actor, not always accepting
So what is a medium-sized builder? It's a searcher, right? What is a searcher is one that specializes in a specific subset of the overall world state. Now, searchers nowadays, they specialize in individual contracts or individual strategies, but they can specialize in individual rollups. And so in some sense, you're just moving up the stack of abstraction, and you have the mega builder, but within the mega builder, there's sub builders, which you could call rollup searchers. And then within these rollup searchers, you have contract searchers that work on a contract by contract basis, for example. So yeah, I do expect that PBS extends further, to builder searcher separation, and as you add more and more levels, it is fine for relatively less sophisticated entities to specialize in one thing and be very good at that. And actually, that's what we see in practice. So what tends to happen is that searchers, there's no searcher that's good at everything. Every searcher tends to be good at 1 or 2 things, and there's 100 searchers, and then as a group, they build optimal blocks. Okay, we have about 20 minutes, so I'll use that to talk about base sequencing, which in some sense is the big finale of this vision. So we have part 1 and part 2, which in some sense is orthogonal to this last part. So if you think from the point of view of a rollup, there's kind of 2 resources that you're consuming from Ethereum. There's Ethereum settlement and Ethereum data availability. And the claim that I'm making today is that there's actually a third resource that you have the option to consume if you want to as a rollup, and that is Ethereum sequencing. And the reason I put this little new emoji is because, you know, it's kind of this mental unlock where you realize, yes, this is something I can go consume, but actually it's been there from Genesis. It's been there all along. And it's only now that we've realized that you can consume it. And in some sense, this is similar to Ethereum data availability, right? There's cold data, and for many, many years, like half a decade, people didn't realize it could be consumed by rollups. And then suddenly we realize, yes, rollups can consume that for data availability. Now the question is, like, why would you want to consume Ethereum sequencing? And basically, in some sense, the answer is very similar to why you would consume settlement and data availability. So you get best-in-class security, you get best-in-class credible neutrality. Credible neutrality is especially important with shared sequencing because you want some sort of sequencer where every rollup and their competitor feels comfortable opting in. So Arbitrum and Optimism and whatever, Base and Scroll, let's take an example. Let's say that Arbitrum launches a shared sequencer and they say, okay, our sequencer is like credibly neutral. Well, guess what? Like Scroll is going to say, well, you built it. That alone makes it non-credibly neutral. And so the fact that we have this sequencer, which has existed since day one, it has the same branding as Ethereum, it has the same security, is a big upside. And then I think a really cool unlock is that not only can we have synchronous composability across the rollups, but we can have synchronous composability with the L1 as well. Now, if you really zoom out and you look at the big picture of TVL, the vast majority of TVL is on the L1. So there's about $500 billion, $500 billion of TVL on L1 with ETH, with ERC20s, and with NFTs. And if you look at the next kind of largest sequencer by TVL, that's the Arbitrum sequencer, I think they have on the order of 10 billion or 20 billion. So it's like orders of magnitude, between 1 and 2 orders of magnitude less than L1. And there's these network effects that with TVL and shared liquidity. And so I think we're potentially going down this dangerous direction where in order for the rollup to be successful, they kind of need to start eating into the TVL of the L1, and you start breaking these network effects, especially when you have these like super linear economic effects, like like the quadratic effect of I forget the law, Metcalfe's law. There you go. So Metcalfe's law is a very simple model saying that the economic value grows quadratically with the number of nodes or the number of some size, some notion of size. Anyway, this is why I claim that using Ethereum sequencing is valuable. And now the question is, like, can we actually do it concretely in practice? And also, can we do it without a hard fork? And I think the answer is yes to both of these questions. We can have rollups consume Ethereum sequencing as a shared sequencer, and we can do it today without a hard fork. So how do we do it? Well, basically, we have a subset of the L1 proposers. So this is where the L1 comes in, that opt into becoming shared sequencers. And the way they do so is by exposing themselves to slashing conditions. So they put forward collateral, and they become shared sequencers in this protocol. And so if you look at the look ahead, there's 32 proposals in look ahead, and only some subset of those 32 will be shared sequencers. So for example, imagine the proposer at slot n+1 and the proposer at slot n+31 have exposed themselves to these slashing conditions. Now, those who have not exposed themselves to slashing conditions, we're going to give them a different name. We're going to call them includers. And the sequencing rights are going to be given to sequencers, as we'll see. So let's say you have a user at slot n who wants to get a pre-confirmation from this new set from basically the based sequencer. So what they do is that they communicate with the first sequencer in the look ahead. So that would be the one at slot n+1, and they get the request and promise from them. And then once they have this promise, what they can do is that they can share it, like some party can share it with the includer at slot n, and the includer at slot n can immediately settle it. So even though at slot n, none of the sequencing rights are given to that proposer still has the option, if they want to immediately include and settle transactions. So what I expect in practice is that you're going to get a 100 millisecond pre-confirmation and basically next slot settlement, which is optimal for Ethereum. And yeah, this is the same picture that we had. Like, how do we modify MEF boost? We basically have these promises shared upstream to the builders that will constrain how the blocks are built. And one of the things I want to highlight here is that when the sequencer is a proposer, there's a bit of a potential problem, which is that the L1 proposer is running on a Raspberry Pi, is like very decentralized and has a very small amount of resources. Like, how can they be a sequencer? Because we said that a sequencer, they need to be running all these full nodes. At the minimum, they need to have enough bandwidth to support, thousands, tens of thousands, hundreds of thousands of transactions per second. They need to have very high uptime, very, very low latency, all of these things, which goes against them being running on a Raspberry Pi. And so this is where the idea of execution tickets comes in. So there's this great write-up by Mike that I encourage you to look up. It's ET execution tickets, hence why there's this alien. And the idea of the execution ticket is that there's a new entity called the execution proposer who explicitly opts in to buying the execution tickets. And when they win the execution ticket lottery, they are the L1 execution proposer. And they can be extremely sophisticated because they've actually opted in to buying these tickets. And then the validators can no longer be responsible for sequencing at L1, and everything is good. But this requires a hard fork. And so we need some sort of solution in the short term. And the solution that I'm proposing here is basically to introduce a new entity called the pre-confirmation gateway. Matthew came up with this name, the gateway, and I guess it's a distinguished name from Relay. And the idea is that the proposer who has sequencing rights here is delegating their sequencing rights to the gateway. So the gateway has the sequencing right. So for example, the proposer ahead of time kind of signs a message saying, I'm giving my sequencing rights to this gateway. And now the users, when they want pre-confirmations, they go and interact directly with the gateway. And then again, just like before, the gateway kind of interacts with the relays and then ultimately behind the scenes, the builders. And so now the gateway is collateralized against safety faults. And there's this edge case that we need to handle, which is liveness faults. Because now there could be, whenever there's a liveness fault, we don't know who is at fault. Is it the gateway that's at fault, or is it the proposer that's at fault? Because now there's like two entities that need to collaborate in order to honor the pre-confirmations. And it turns out that this can be solved with trust in the exact same way that there's a trusted relationship between the proposer and the relay. So in MEF boost, the proposer is actually trusting the relay to be online for the get payload request. So basically, there's this potential edge case where the relay responded to the header, the proposer signs the header, and then the relay goes offline, in the few like milliseconds, and then they can't respond with the header, with the payload. And it's the exact same thing here. Basically, the gateway signed all these preconfirmations, and then they go offline just before the proposer is meant to propose that block. And so now the proposer can't honor these preconfirmations. And basically what I'm suggesting is that we have a similar trust relationship between the proposer and the gateway. And actually maybe the most natural solution here is to collapse these two and have the gateway be a preferred relay by the proposer. So I believe that the relays are already like very well suited to be a gateway here. Now I have one final slide, but I only have 10 minutes, so I'm happy to answer questions now, or go to the final slide. I guess my final slide is a bit of a philosophical one, which is that we have sequencing that we need to solve as a community. And I think we all agree that we want to move to decentralized sequencing. And the vast majority of open problems from a technical standpoint are specific to decentralized sequencing. Now, within decentralized sequencing, there's some problems that are specific to shared sequencing, right? Shared sequencing is a specific type of decentralized sequencing. And then even more specific, we have base sequencing, which is a special type of shared sequencing. And I believe that most of the problems, let's say 80% of the problems, are specific to decentralized sequencing. You have to handle MEV, mempools, intents, OFAs, preconfirmations, data compression, all of these things. And then with shared sequencing, like there's a few new problems that come up, but most of them are specific to decentralized sequencing. So one very good example is MEV sharing. When a rollup opts in to a shared sequencer, they are basically giving away MEV to the shared sequencer. And one of the things that Espresso is working on is identifying where the MEV originates from and kicking it back, kind of giving it back to the rollup that created it. So with shared sequencing, you have new problems like MEV sharing, and that's something that's being tackled. There's also something called deposit sharing, which is this really cool idea by ZK Sync, which is that if you have two rollups and you want to do withdrawals and deposits across these rollups, well, it's kind of wasteful to go through the L1 every single time. And so what if we had a shared deposit contract where all the assets were deposited, and now whenever you do a cross rollup transaction, you don't touch the L1, it's all settled through the L2, and it's extremely cheap and efficient from a gas perspective. And then there's this idea from Polygon, which I briefly mentioned ahead of time, called the aggregation layer, which gives you this level of safety for cross rollup bundles. And then there's the base sequencing, which I kind of went through the design here, and in some sense it's only opinionated on one thing. It basically says that the very end of the MEV pipeline terminates with the L1 proposer. And the cool thing is that most of the problems are not at the base sequencing level. They have to be solved at other layers, and there's no fork required. And that's the end of my presentation. And we still have a few minutes for questions. Lynn.
So I have a question about the includer that you mentioned.
Yes.
So when you say the includer settles, you mean that they settle as in like the L2 state root?
Correct, yes.
Okay. So in that case, if the preconfer lies about the position, not only is the preconf invalid, but the settlement will be invalid. Or then in that case, what would happen?
Right. So the sequencing rights are given to slot n+1, and the sequencer says, I'm going to promise to put transactions A, B, C in positions 1, 2, 3. And then these promises are gossiped. And so now it's perfectly safe for the includer to go settle transactions A, B, C at positions 1, 2, 3, because that's what the sequencer said they wanted to sequence. Now, one of the things that is definitely possible is that the sequencer equivocates, right? Like they made promises for transactions A, B, C, but then it turns out they also sign off transactions A prime, B prime, C prime. And in that case, they would get slashed for a safety fault. And the includer would have the option, if they're aware of both of these, they have the option to either settle ABC or A prime, B prime, C prime. It's up to them what they want to settle. In either case, they're completely protected because the fault came from the sequencer, not from them.
See.
Lisa.
Do we have any constraint on how many blocks from different rollups each gateway can promise?
Right. So let's say that we're in this situation. We're in slot n, and the next proposer is in slot n+1. Then actually the proposer can make promises for 2 slots, right? They can make promises for slot n and for slot n+1. So in some sense, they can cover 24 seconds worth of MEV and 60 million gas at most. Now, one of the things that you need to be careful of is making sure to not overpromise. So because this sequencer only has 60 million gas to work with, they shouldn't promise more than 60 million. If they were to promise 70 million, then they're guaranteed to get slashed. Now, another thing that they need to make sure is only start providing promises for 30 million gas and above after the includer has included the first batch of promises. So yeah, what the sequencer needs to do is basically provide a small tip to incentivize the includer to settle the transactions, so that now they can start providing preconfirmations for 30 million gas and above, between 30 and 60 million gas.
So we can end up, if there are not too many gateways, we can end up in the situation when there are blocks from rollups who have to wait because we just don't have gateways within these 32 that are defined.
Great question. So are you saying that it's possible that in the look ahead, which is 32 slots, there's just 0 shared sequences, there's none of the proposers here have opted in, and so basically there's no sequencer. In which case, preconfirmations break down. Now, one of the things I do want to highlight is that the includers, in addition to settling transactions that have been sequenced and pre-confirmed, they also act like an inclusion list. So they can just include arbitrary transactions that have to be executed by the end of the slot of this executor. So for example, if this shared sequencer is censoring for whatever reason, well, the includer here can make sure that any transactions that are being censored will go in here and therefore will get executed by slot n+1. Now, in terms of making sure that there's at least one pre-confirmer in the look ahead, you need about 15% in order to have high probability that there will be at least one pre-confirmer and shared sequencer in the look ahead. One of the things that's, I guess there's 2 things that are good news. One is that it's very easy to change the look ahead. We can change it to 64 slots or 128, and that's just a constant. That's a super easy hard fork. The other thing I'll mention is that there's actually an incentive in the very early days to become a shared sequencer. And the reason is that you get to control many slots, and therefore you get lots of MEV for these rollups. So for example, here, this shared sequencer would get 2 slots of MEV, and this one here, assuming this is all gray, would actually get 30 slots of MEV. So in the very early days, you're making a ton of money from MEV because you're one of the few providing the service. And another, I guess, piece of good news is that 15%, potentially can be handled by one actor. So if Coinbase, for example, says, we're, from the goodness of our heart, we're going to bootstrap this pre-confirmation infrastructure, even if there's going to be very low fees or whatever, like they can single-handedly do that. Or maybe Lido could help out with the initial bootstrap.
Yeah, makes sense. Thank you.
I still have a question about the includer. So when there's a transaction ABC and the preconfirmer preconfirms ABC, but actually posts the data of A prime, B prime, C prime, which one is the canonical? Like, which one is the correct history?
The includer can only settle transactions if they've been signed off by the sequencer. So if they say, please include A prime, B prime, C prime, then they can force inclusion, just similar to an inclusion list, if there's censorship, for example, but they can't guarantee that A prime, B prime, C prime will be in position 1, 2, 3. That will be up to the sequencer to choose the positions of transactions A prime, B prime, C prime.
So if they don't do A prime, B prime, C prime, then
that is a slashing violation. So that would be a liveness fault, because they wouldn't be able to build a block which satisfies the inclusion list, and therefore it would have to be like some sort of empty slot, from the point of view of the rollups, and they would get slashed.
So that batch will be invalidated in that case.
Yes, I mean, there's a bit of a design detail here, which is that if the shared sequencer kind of has a liveness fault, like do you execute the transactions in the inclusion list, or do you just trash them? There's reasons to do both, either. Like one reason to do it is that you have more of a liveness guarantee and better censorship resistance. But a reason to not do it is that now you're having MEV within the inclusion list itself. I mean, maybe the best design is to keep them around, but now put the constraint on execution on this shared sequencer, basically the next shared sequencer.
I see. That makes sense. Thanks.
Okay, amazing. I think we're actually at time now. There is a dedicated call for base sequencing and pre-confirmations with about 100 people in it. That's happening every couple of weeks. So do let me know if you want to join these calls. There's already been 3 calls. They're all recorded on YouTube. There's also notes, and there's also a Telegram group if you want to join that as well. Thank you so much for your time, and looking forward to chatting more.
Thanks. See you.